Okay guys, this is a quick tutorial to help you to get your head around how to calculate the relative atomic mass of an element on the periodic table based on the relative abundance of its isotopes. So we've got an example for you to take a look at here. First one, we've got rubidium. It's got two isotopes, rubidium 85 and rubidium 87. So if the abundance of rubidium 85 is 72.2 and the abundance of rubidium 87 is 27.8, what is the average atomic mass of rubidium? So first things first, we can see that we've got rubidium 85 with an abundance of 72.2. We can see then that we've got our rubidium 87 with 27.8. So we times them together, and what we should have is 6137 and 2418.6. Quite dog. Okay, now when we add these together, what you should find is that that comes to 855.5.6. Now you need to bear in mind that what we've got here as well is that this is the actual abundance, and it comes to 100%. Okay, so if we add these two together, we will have 100%. And because we're looking at the average, we need to take a look at the average of the of these two isotopes. So we'll divide that by 100, and that will give us what our relative atomic mass of rubidium is going to be. What you should hopefully see is that that's going to be 85.56. There's the first one sorted. Okay, let's take a look at another example, help you get your head around how to do this. So we've got uranium this time. Uranium is used in nuclear reactors. It's a rare element on Earth. It's got 3 common isotopes, and the abundance of uranium-234 is 0.01. So we've got the 234 at 0.01. We've got uranium-235 at 0.71. And we've got the uranium-238 at 99.28. Okay, so it's a simple case of multiplying those 3 together. What we should have is 2.34 and 166.85 and 2368.64. We add those together. What we're going to have then is 23797.83. Trust me, you can work it out in your calculator a bit later to see if it all makes sense. Like we said earlier, this is the what 100% of the relative abundance on the planet went up to. So we divide it by the 100%. What you should then find is that the relative atomic mass, or the average atomic mass of uranium, comes out at 237.97. There's your answer. Let's take a look at a third example. So this time, titanium has 5 common isotopes. It's got titanium 46 with a percentage of 8, titanium 47 with 7.8, titanium 48 with 73.4, titanium 49 with 5.5, titanium 50 with 5.3. So we take each one with its relative proportions. So titanium 46 times 8.0. We've got titanium 47 times 7.8. Got titanium 48 times 73.4. We've got titanium 49 times 5.5. And we've got titanium 50 times 5.3. Same again, add these together, times these together. What you should get when you stick it into your calculator is 368. 366.6, 3523.2, 269.5, and 265. So if we add those all together, what you should come to is 4792.3 over 100, which means that your relative atomic mass of titanium is going to work out at 47.92. There's your answer. So it's pretty straightforward to do. Don't let it freak you out when you see it in your exam. The next example is asking you, why is the mass in atomic mass units of carbon-12 of a carbon-12 atom reported as 12.11 in the periodic table of the elements? What you've got to remember is that carbon-12 is the most abundant form of carbon, but carbon does come as carbon-12. It comes as carbon-13, and it comes in extremely small proportions of carbon-14. So because carbon-12 is by far the most abundant, that means that its atomic mass is going to be much closer to 12 because of the relatively smaller proportions of 13 and 14. But if we knew what the percentages of 12, 13 and 14 were, we could work it out using a method just like we did up here. So hope that makes sense to you, and it's helped you to refresh your memory of how to work out the relative atomic masses based on the relative proportions of the isotopes. So don't let it stress you out. If you want to watch this again, watch it again, pause it at the various calculations, test yourself and make sure you can do it on your own. Okay, cheers for watching, bye.